The title of my talk is Young Galaxies at All Times, which I realize is very confusing as a title. So let me explain right away what I mean by that. Oh, I'm sorry. Is that better? Okay, sorry. All right, so one of the big questions astronomers are trying to answer is, how did our universe come to be? And so an important part of understanding how structure evolved in the universe is understanding how galaxies evolved in our universe. And so in order to understand the evolution of galaxies, just like Rachel explained to us, we want to be able to understand the very first galaxies that formed in the early universe, the galaxies that we think are the building blocks for the more massive evolved galaxies that we see today. However, these very early galaxies are very far away, which means they're extremely faint. So not only is it really hard to study their properties in a lot of detail, but generally they're pretty hard to find. And so what I'm interested in doing is finding the most pristine and unevolved galaxies in the nearby universe in order to be able to study the early universe in a lot of detail. All right, so now let me take you on a brief journey through the history of galaxy formation in the universe so far. All right, so about 200 to 300 million years after the Big Bang, the first galaxies formed. These were very small dwarf galaxies. And so as the universe continued to evolve, some of these galaxies merged and or interacted with other small galaxies. And these formed bigger galaxies, and these interactions fueled more rapid star formation. And about 3 billion years after the Big Bang, you start to see a ton of these big blue galaxies. They're blue because there's a lot of UV light coming from a ton of new and active star formation from these early mergers and interactions. And so you can see as we move into the present day, there are less and less of these big blue galaxies, indicating that star formation is shutting off in galaxies. And so what you see are a bunch of big galaxies with a variety of colors left behind from this actively star-forming era. All right, so the evolution that I just explained in this video actually can be summarized pretty well with this plot. And so in this plot on the bottom axis here, we have the age since the Big Bang. And so on this end, we have, this is current day. And as we move this way on the plot, we're moving further back in time, or further away from us. And on the y-axis, we have the star formation rate per unit volume. So basically, this plot is showing us the rate at which stars formed as a function of time. And so you can see that in the early universe, over here, we have a buildup of star formation until this peak at about 3 billion years after the Big Bang, and then a steady decline into the present day. And so this is a trend we've actually been able to measure from observations of galaxies, but in order to understand this trend that we observe, we need to answer a couple of questions about this plot. The first being, why is star formation shutting off in the current universe? And also, what were the properties of the very first galaxies that we know were the building blocks to the more evolved galaxies that we see in the more nearby universe? All right, so to answer these questions, I'm utilizing several instruments at McDonald Observatory in West Texas. So the first being on the 2.7 meter telescope, I'm using an instrument called the Mitchell spectrograph. And then way in the back, we have our 10 meter Hobby-Eberly telescope, or the HET. And on this telescope, we have an instrument called VIRUS, and this instrument was built for the Hobby-Eberly Telescope Dark Energy Experiment, which if you guys have gone to other Astronomy on Tap talks, you have maybe heard a little bit about that. And there's also another instrument on this telescope, LRS2, so this is a second generation low resolution spectrograph. And so there's a reason I'm using all three of these instruments. They all have something in common. So all of these instruments are integral field spectrographs. So what is that? So just a brief review of how a traditional spectrograph works. So with a traditional spectrograph, you place a slit over the object that you're observing, and the light from your object enters the spectrograph, gets diffracted off a grating. So basically the light gets broken up into its color components, much like light going through a prism, and what you get is a single spectrum for the object that you observed. So an integral field spectrograph is very similar, but instead of placing a slit over your object, you actually place a bundle of fibers over your object. And so in this image, so this is representing the field that the telescope is looking at, so this galaxy, and each of these boxes represents a fiber on that field. So you take all of these fibers and you line them up along the slit of your spectrograph, and then it works very similar to this traditional spectrograph where the light goes through the spectrograph, gets diffracted off a grating, but this time, instead of one spectrum for your object, you get a spectrum for each one of these fibers. So essentially what you get in the end is a spectrum for each spatial region on the field that you're looking at. So essentially with an integral field spectrograph, you get both spectral and spatial information at once. So these instruments are super cool. They're basically the perfect instruments for studying the detailed properties of galaxies and also for blindly surveying the sky for faint sources. All right, so now back to our questions. So for the first question, we want to understand the mechanisms that are shutting off star formation after its peak. So we have some ideas as to why this could be happening. We're not completely clueless. So we know that star formation is fueled by cold and falling gas. And we also know that when a galaxy forms a ton of stars, it blows out a lot of gas through supernova and stellar winds. And this is a problem because galaxies need gas to continue to form stars. So what I want to do is be able to measure how much gas is being blown out of these galaxies from star formation to be able to better understand the impact that these outflows have on the amount of gas that's available for later star formation. So ideally, we would want to study galaxies here at the peak when they were most actively star forming and blowing out a lot of their gas. And so, however, this is kind of difficult because these galaxies are really far away, they have a really small angular size on the sky, and so they're very faint. And so it's hard to study these processes in a lot of detail in these galaxies. And so what I want to do is find a galaxy that's very nearby, that's still actively forming stars like these galaxies at this peak. So lucky for us, we actually know of one. There's a galaxy called M82, and it's very nearby. Only 10 million light years away. And so this is a picture of what this galaxy looks like. And so over 50 years ago, Linz and Sandage announced that they discovered an explosion in the center of this galaxy. And so this explosion that they described was later understood to be caused by massive amounts of star formation happening in the core of this galaxy. And so the massive amounts of star formation are blowing out a ton of gas really rapidly, which you can actually clearly see in this image. So the blue part here is, oh, there it is. The blue part is actually the disk of the galaxy, so it's a very edge-on galaxy. And these red cones you see above and below the disk, these are actually the outflows, or the gas being blown out from the star formation that's happening in the core. So one question you might ask is, why is this happening to M82 so late in its life? So this is M82 over here. So we know that M82 has recently started interacting with its neighbor, M81. So the gravitational interaction between these two galaxies has stirred up a lot of gas in M82, causing this gas to collapse and form a bunch of stars really rapidly. And so what I want to do is use M82 as a local laboratory for studying these starburst-driven outflows in a lot of detail. So I want to be able to map the outflows in a lot of detail in order to measure the amount of gas that's escaping the galaxy. All right, so to do this, I'm using, again, the Mitchell spectrograph on the 2.7 meter at McDonald Observatory. So I told you before that this is an integral field spectrograph. However, it's a very special integral field spectrograph in that the area that this instrument can look at is about 100 times larger than nearly any other instrument of its kind, making it really the only integral field spectrograph I could reasonably use to map the entire extent of M82's outflows. All right, so back to this picture. So this is the same picture I showed you before. So this is actually an image of M82 taken with the Hubble Space Telescope. And so in this image, you can clearly see that these outflows extend to about 6,500 light years above the disk. So if we zoom out, so this is the map that I was able to create with the Mitchell spectrograph. So you can see that the outflows clearly extend well beyond the 6,500 light years above the disk. So this is the disk down here. So the main part of the outflow extends to about 20,000 light years above the disk. You can clearly see an arm under here that extends to about 30,000 light years above the disk. And I've been able to map the outflows out to the cap at about 39,000 light years. So over several observing runs with the Mitchell spectrograph, I've been able to map the outflows of M82 more extensively than it has ever been done before. And so with this, I'm going to be able to more accurately measure the amount of gas that's escaping this galaxy, and that's going to help us better understand this mechanism that might be shutting off star formation in galaxies. All right, so studying M82 gets us closer to understanding one of the main mechanisms that we think is a contributor to the fall-off of star formation, so this decline. But if we revisit our second question, so what were the first galaxies like? So studying M82 helps us better understand galaxies up here at the peak. But another question I have is, are there galaxies in the nearby universe that have remained unevolved for long enough to be analogs of these very early galaxies, the ones back here? So, and by early galaxies, I mean galaxies that formed less than 1 billion years after the Big Bang. All right, so now what do we know about the galaxies here at the end of this plot? So, luckily for us, we have been able to find a few of these galaxies. Here's example images of these galaxies. These aren't lens, these are just ones that we found the normal way, I guess. So the galaxies are these little blobs between these red lines here. And so even though these are really faint and far away, we've been able to learn a little bit about them. So we know that these galaxies are very low mass, they're very compact, and they emit this special line called Lymanalpha. So this is an emission line that comes from hydrogen. And so basically we know that this line is emitted in the UV part of the spectrum, and we know it comes from young stars, and we also know that it's very easily obscured by dust. So the fact that these galaxies are emitting Lymanalpha tells us that they're actively forming stars, and that they also have relatively little metals and dust, which means they haven't been forming stars for very long. And that makes sense, because these are very young galaxies. And so my question is, can we find analogs of these galaxies, so galaxies that have similar properties to these early galaxies, but in the very nearby universe? So in 2009, there was a survey of the nearby universe called the Sloan Digital Sky Survey. And basically this survey made a giant image of the entire sky. And so they enlisted the help of the public to try to classify the galaxies that they found in this survey. And one of the things they found were these tiny, compact galaxies that appeared green, hence the name green peas. And they wanted to know what these were. So they followed them up with spectra. And what they found was that these galaxies emit a really strong oxygen line in the green part of the spectrum. So this is why these galaxies appear green. And so much like Lymanalpha, this really energetic oxygen line tells us that these galaxies are actively forming stars and that they have relatively little dust. And then a later follow-up of these galaxies in the UV part of the spectrum found that they actually do emit Lymanalpha. So basically these galaxies are low mass, they're very compact, and they emit Lymanalpha. So the neat thing about them is they're very similar to these early type galaxies. So they found these galaxies, so the survey found these galaxies at about 3 billion light years from us. And so because of the limits of the survey, they weren't able to find them any closer. And so what I'm interested in is if we can find galaxies like this, but even more nearby. All right, so earlier I told you guys that I was going to use VIRUS, an instrument on the Hobby-Everly telescope. So VIRUS is the instrument that was built to conduct the Hobby-Everly Telescope Dark Energy Experiment, or HATEX. So we know HATEX is designed to find nearly 1 million Lymanalpha emitting galaxies from 1.8 to 3.5 billion years after the Big Bang. So HATEX is going to use these galaxies to map large-scale structure in the universe in order to try to understand dark energy. And so to find all of these galaxies, HATEX is surveying a really large patch of sky blindly. So it's a patch of sky about the size of the Big Dipper. And so because it's surveying this really large patch of sky blindly to find these really far away galaxies, we would expect that in that survey they're going to find some nearby galaxies too. And so what I'm interested in doing is using this survey to find the closest galaxies that are emitting this strong oxygen line, like these green peas. And so for people trying to study dark energy with HETEX, they consider these nearby galaxies emitting oxygen to be contaminants of the survey. But for me, those are the ones that I want to find. So because they are closer than the green peas, they're actually going to be emitting this oxygen line in the blue part of the spectrum, hence the name blue peas. It's not a great name, but I'm open to suggestions. So this is actually an example spectrum of one of these galaxies that we've already found, but I'm hoping to find nearly 100 of these galaxies in the HETEX survey and build up a sample of local analogs of the earliest galaxies that we can study in detail. All right, so with HETEX, I'll be able to find these galaxies from about 11.8 billion years after the Big Bang to present day. And so this will be the most nearby sample, I guess, of these of analogs of these early type galaxies. All right, so now what about all of these Lymanalpha emitting galaxies that HETEX is going to find here at earlier times in the universe? So because these galaxies are emitting Lymanalpha, that tells us that there's still probably good analogs of the earliest galaxies like these blue peas. However, because they're a lot further away, they're going to be much smaller on the sky and they're going to be fainter. So we're not going to be able to study them in a lot of detail like we will these blue peas. However, with this survey, we're going to find nearly 1 million of them. So we won't be able to study them in as much detail as the blue peas, but the sheer number of them is going to allow us to make a statistical study of their properties compared to galaxies at the same distance. So these are examples of 2 of these Lymanalpha emitting galaxies we've already found in the HETEX survey, and we're hoping in the next 5 years or so we'll have nearly 1 million of these galaxies. All right, so I spent a lot of time in this talk talking about finding analogs of the earliest galaxies in the very nearby universe. But one thing you might be asking is, will we ever be able to study the earliest galaxies directly despite them being so faint and far away? So Rachel provided one answer to that question with gravitational lensing, a special technique for finding some of these galaxies. Another answer is in the next generation of telescopes. So Rachel talked a lot about the James Webb Space Telescope. It's like the newer, bigger Hubble, and also the upcoming generation of extremely large telescopes. So a couple of them being the 25-meter Giant Magellan Telescope and the 30-meter telescope. So basically bigger light buckets for finding fainter things. All right, so now just a brief summary of the things I talked about. So studying M82 with the Mitchell spectrograph provides a nearby laboratory for studying processes that are shutting off star formation since 10 billion years ago, but in a lot of detail. The sample of blue peas we will find in the HETEX survey will provide a sample of the closest analogs of the earliest galaxies that can be studied in great detail. However, we expect that these galaxies are going to be relatively rare in the nearby universe, and so the massive sample of Lymanalpha emitting galaxies that we're going to find in HETEX are going to allow us to make statistical conclusions about their properties. And lastly, the next generation of telescopes will allow us to study the sample of the earliest galaxies directly. All right, thank you.
Thank you, Feedback Fighter. All right, let's take some questions. Saw the first hand there, gentleman in the middle.
Sorry,
Theoretically, do galaxies die?
Theoretically, do galaxies die? So I guess they don't like burst apart, but eventually there are examples of galaxies like red and dead elliptical galaxies, we call them. Basically, they run out of gas to form stars. So essentially, they still exist, but they're not really doing much anymore, I guess, if that answers your question.
Mm-hmm. Yeah, that's good. Right there.
Yes, it'll be at L2.
Yeah.
So basically, it'll be at the point. So if the sun is here and Earth is here, it'll be behind Earth. So it'll always sit behind Earth as Earth orbits the sun. So, yes.
The question was, will James Webb Space Telescope be at a Lagrange point? The answer All right, let's take Feedback Fighter one more time.